put the brackets around it?
So, we're close to midterm break, so you have academic development next week, so there's no class, just in case you forgot. So last week we covered correlation, least squares regression, logistic regression, and today we go back to ANOVA, but we go to 2x2 ANOVA, 2x5 ANOVA, 2x3 ANOVA, basically two-way ANOVAs. So interaction effects, you might have done some also in your undergraduates, but we'll return to those today. The goals for today are that we refresh what you should know by the assumptions of ANOVA, so homogeneity, variance, normality. So that's the assumptions underpinning ANOVA, and then you sort of know how to do a two-way ANOVA and how to make plots, and also for like continuous interactions, continuous categorical interactions, and categorical like factorial interaction ANOVAs. So the assignments. After today, you should be able to complete the following sections: the two-way ANOVA bit in your assignments, plots, and some of the plots you could already do because none of the plots we're doing are, again, it's violin plots and scatter plots. So in principle, you should be able to do them already, but I'll show you some alternative ways perhaps to do them and some ways to further beautify them. And after today, you can complete the entire assignment. So that's probably how you're all feeling. So there's easy marks to gain throughout the assignment. So if you get stuck, my advice is if you really are losing hours and hours, just move along to something else because it's chunked. So if you really get stuck with correlation, move on to the bit on logistic regression. Or if you get stuck with one of the ANOVA bits, move on to the other thing. If you can't make a plot, do something else. And perhaps that will keep you motivated to work your way through it because every section you'll see has marks allocated to it. So also don't panic if you can't complete a single, if you can't complete a small thing, because you have enough things to capture a high mark. But in principle, you should be able to do everything. Again, I would advise you. So some of you have consistently submitted all the exercises, and I think that will really help you to work on the assignment because the exercises map onto what you have to do in the assignments. So if you haven't done so, I would really recommend rather than going into the assignments first submit the exercises, work your way through the exercises. After you've done that, I'll send you a link so you can check the solution against your solution, and from that you will hopefully understand how to tackle the assignment. And so, as before, any questions in the discussion board? So some of you have already posted some questions. I'll do my best again to answer quite fast, but don't leave it too late. Perhaps. Too much to iterate, but too much iteration. But I won't be answering questions like 5 minutes before the deadline or like 24 hours. So really, it's my birthday on that Friday. So don't wait until the very last minute to submit questions on your assignments. Also, because things might go wrong with Blackboard or something. So you really have enough time to plan in advance. So don't leave it till the last minute. As with your thesis, as with everything, just in life, tax returns, don't leave it till the last minute. Any questions thus far on the procedure? All the instructions should be fairly clear. So before we move to ANOVA, it's important that we talk again about types of errors. I talked a little bit about it last time, you might recall, and hopefully it will become clear. So initially, you should know that ANOVA was designed for fully balanced designs, so equal numbers of cells. And equal n for each factor. So that was the original experimental design for those type of studies. Now in reality, often that doesn't really happen because we do random allocation. That means that some conditions have a lot more cases and some have a lot fewer cases. Or you end up removing certain outliers before you analyze them. So you might not always have perfectly balanced ANOVAs, and that matters. So if everything's perfectly balanced, then some of the assumptions for ANOVA are relaxed, so you don't have to worry as much. But for when there's unbalanced, there are different types of ways. So if you have a perfectly balanced thing, this really doesn't apply. There's different types of squares. But in reality, most of you will have unbalanced designs, and so then it matters to have that you have different types of sums of squares. So you might recall there's type 1, type 2, type 3. and R uses type 1 by default, and so SPSS for most things uses type 3 as default. So the means are mean, but are they balanced? So are they balanced across their factors? So that's a question to ask you first. So if you have an entirely balanced design, then you don't necessarily have to worry about these type of things. You can just calculate any type of interaction. In principle, it should give you the same type of conclusions. So type of errors. So if everything is uncorrelated, and as in A and A, it's not as large as you can see, but you can see back to Venn diagrams. Yeah. So if you have the sums of squares related to A, the sums of squares related to B, and the sums of squares related to A, B, the interaction. So if they're completely orthogonal, or like if they're completely uncorrelated, you shouldn't worry. But in reality, most of you will have cases where they are correlated, and so these Venn diagrams, these circles, these overlap. So sums of squares of A, B, and A, B will overlap. And then there are different ways of calculating the sums of squares. It has to do with the degree of overlap in U, V, W, I, Y. It has to do with that type of overlap and how you handle that. Whether you first, for example, want to do the entirety of A and the entirety of B and then look at this, or if you just want to look at chunks of it separately. And so that's basically what the sums of squares is all about. And you can read more about it in detail. So this is just very broad highlights. So type 1, the type that R uses by default is sequential. So it's order dependent. So you put in A in the first order, so everything related to A, and that's T plus U plus V plus W. That's if we go back, I'll actually move forward so you can see it sort of here. So this one just puts this circle first, and then puts the other one. And so then it would put X plus Y, and then after that it would do the other one, the remaining Z in terms of sums of squares. Yeah. So that's order dependence. It's sequential because it first does A, and then it does B, and then it does the A times B interaction. Type 2 is hierarchical, and so it first does T and W, and then it does X plus Y, and then it does Z. So it adjusts for terms all other except the higher order interactions for those same predictors. So this is quite good, as we'll discuss later, for main effects, but not necessarily good for interaction effects. And then type 3, which is usually the default, it's the most conservative. That's not always the best case because it also means that it might lose power in some cases. So this assesses the contribution of each predictor over and above all the others. And again, you can sort of see the sequential of errors. Yeah. So which one to use? So you have to pick. You have to actually think about the type of analysis you're doing and the corresponding what it corresponds to your hypothesis. So if you have strong theoretical predictions for A, so you're only interested in A and you want to control B and the interaction, then perhaps it makes sense to do type 1. But most of the time, the choice is between type 2 and type 3. And for the highest order interaction, all of them will give the same. So this is just an example with a 2-way interaction, but you might have 3-way interactions also. I hope none of you will ever do 4-way interactions, but in principle, it goes on, and you can calculate all these different types of interactions. So type 2 is the most powerful when no interaction is present. But note that the interpretation is differently for the main effects in that type of setting because the way the sums of squares are partialed out. And type 3 is the most conservative in terms of errors. So it really depends on the degree to which you want to interpret the main effect afterwards and the degree to which you care about the interaction versus the main effects in this type of designs. Any questions thus far on this? So you might have heard a little bit about sums of squares. Did you hear anything about sums of squares in your undergraduate? It does ring a bell? Okay, good. So interaction effects. Can anybody explain, because I've been just banging on about interaction effects, what interaction effects really are all about? What is the interaction effect? No? If you've calculated an interaction for some things in your design, did you have like a thesis with an interaction effect? So one of you must have had like a thesis with an interaction design, Or none of you had any interaction designs, everything was main effects? Everything main effects? Okay. So basically interaction has to do that we think that the effect of one variable is conditional upon the effect of another variable. And that's often the case especially in social psychology, which is a field where I'm also working, where you have, for example, a person times environment interaction. So for example, you think that people with a certain type of personality in a certain type of setting, they'll go on to behave very racist, or they will be very nice. But usually it's not just the main effect. You don't think that these people are nice all of the time, but if you put them in a certain setting, then it will lead them to behave in a certain way. So that's the interaction type of effect. So basically, the effect of one variable is conditional upon another variable. And that's often the case in psychology, because we have, for example, in occupational psychology, the person-organization fit. So you think that in certain type of organizations, people will behave differently. It's often the case in social psychology, where you have people in one group behaving differently based on their personality than in another group. And so often we have designs or questions which have to do with interactions, where we think there's not necessarily a main effect, but we think people's behavior or attitudes or scores will change as a function of two variables, so one influencing the other one. Yeah? It also means that there's no straightforward interpretation of one of the effects, because it's conditional upon the environment it's in. So if you think back of the social psychology example, so you might not find any type of relationship in the main effect, but it's conditional only after you put people in a certain type of situation, they'll start behaving a certain type of way. Does that ring more of a bell in terms of why you would want interactions? Yeah? So often you care about those. So synonyms, so moderation or moderation analysis is the other term. So one variable's effect is moderated, so its strength is dependent upon the other variable. That's the same. And moderation is not the same as mediation. Any of you have heard of mediation? Mediation effects? Mediation designs? I saw somebody nodding there. So what's the mediation type of design?
Like saying if one thing helps.
Yes. So when we think of mediations, we have sort of causal chains or causal pathways, or it's hypothesized as causal pathways. So A influences B and B influences C, and sometimes the effect of A is entirely explained by the effect in the middle of B. So the effect of A on C is entirely explained by what's happening in the middle. And we'll talk about mediation analysis later on, but they're not the same thing. And you can have complex things like moderated mediation and mediated moderation. So you can draw out all the things, so you can sort of make predictions that in one group there is a pathway, and the other one there is not a pathway, and that would be an example of moderated mediation. We won't go into those very complex designs, but in principle, you can then combine both of them, and you can have mediated moderation or moderated mediation, and basically use them sort of as a Lego set to build more complex models. Yeah, so moderation is not the same as mediation, but in I think 2 or 3 weeks' time, we'll talk about mediation effects and these causal type of chains. But it's a confusion which people often make when talking. And so you have to think carefully. So when you're hypothesizing or testing things, it usually helps to draw out the type of things you're expecting. So if you have things with causal chains, then usually you're looking at a mediation model. If you have things where the line or like the strength of relationship varies as a function of another variable, then we're talking about moderation designs. And basically, it's the multiplying of terms. So the interaction is nothing more than A times B. So as we saw in the sums of squares example, so multiplying the factors and multiplying the continuous variables to get those scores. Yeah, because that's what the interactive effect is all about. So it's basically the effect of one is conditioned based on the other one, so that means multiplication rather than addition. So if we were controlling for things, we sum them together into a model. When we're calculating interaction effects, we're multiplying terms together in the model. So you might recall also from SPSS that when you did interaction models, you were multiplying A times B, and sometimes you might have done that manually, so you might have made a new variable which is A times B in order to use it in an interaction model. Any questions so far? If I'm going too fast, let me know. So, multiplying. So, before you do a two-way ANOVA, it can be 2 by 2 or 2 by 3, and occasionally I've made the mistake of saying 2 by 2 to anything, which even if it has 5 categories, but that should be a 2 by 5. So basically, this corresponds to the number of categories in the factorial design. And for shorthand, some people also use for continuous variables a 2 by 2 design, even though one is continuous and there's no factors, but the principle would be that there's that you can sort of cut it into a high and low type of score. So that's sometimes also listed then as a 2 by 2 ANOVA. So you would check the relevance assumptions first. Do you recall what the assumptions are for ANOVA? Anybody? I've mentioned them at the start of this session. Come on, people. I know it is early mornings. I don't want to point to people. So think back in the ANOVA thing. What were the assumptions that we tested, and how did you do that?
I don't know what you mean.
You don't know what you mean?
Was it the homogeneity one?
Yeah, so homogeneity is one of them. Homogeneity variance.
Yeah.
Do you recall how you did that?
And the equal. Sorry?
Do you remember how you tested for homogeneity variance?
Plot or something. I don't know.
No, unfortunately, not a. Well, in heteroscedasticity you can use plots, but we've tested homogeneity via certain tests.
Levin.
Yeah, the Levine's test, or I don't know if it's Levine or Levine's, or that's the test we used, and we also saw some other tests like the Bartlett's test and some other examples. So homogeneity variance is one. What's the other one? It also applies to regression. I saw you whispering, so you must have an ID. Come on.
No, I don't have to.
Like, this is a safe space.
Someone help. Normality.
Yes, some normality. So normally we would plot all those things, and we would do that by condition, and you would sort of see if it looks normal distribution, and if it looks normally distributed. And if it doesn't, then we're hoping that either we can make it normal by, for example, transforming it, or we are hoping that we have enough cases for the central limit theorem to help us out and to assume it's sort of robust. And some of these things the reason I've told you about bootstrapping, for example, is that some of these things can be overcome by bootstrapping. So, because then we resample from our own statistics and we don't rely on the normal distribution. We just have the computer drawing samples over and over and calculating the same thing. So we don't have to assume it's normal. Okay? So those are assumptions you should test, and what you typically come across in terms of interactions is these type of plots. So you have, for example, low training and high training, and low and high autonomy, and then you see that one group is going up a lot stronger than the other one, yeah, and the other one is sort of not as strong. And in this case, it's job performance. But often you've seen those things in journal articles, also for your journal club. So these type of plots where one group, for example, has a strong increase. So here in this case, we can't really. So I think this is the high autonomy one. I asked for a new beamer, so it's in terms of resolution. But it's just these type of plots should be familiar to you, and that's how people display interactions. Yeah. So talk a little. So form groups of 2 or 3, and talk a little bit about. So apparently none of you did interactions, but I think that's quite hard to believe. So you must have come across an interaction design either now in your internship or somewhere else. And if not, think of a case where you would have an interaction, and then think about the shape it would be. So we've looked at one shape, but there are other shapes as well. So we had one group going up and the other one going not up as not increasing as fast. But there's other constellations you can think of. So spend some time just now talking to your neighbor, and I think there might be one group of or a couple of groups of 3, and think about your interaction design. And then I'm going to ask a couple of you like what type of interaction design you think it would be, and what's the shape of it. So is it what would it look like? So if you would draw it out, what would the lines look like? Yeah. Chat away.